So the Arctic is a region of our planet which is undergoing profound changes at the moment. We see a retreat of the sea ice and we see some of the strongest warming on the planet. And the CIMR mission is there to try to document these changes.
CIMR is the largest radiometer ever developed by ESA.
I would describe it as a dream come true. For decades, scientists, engineers, technicians have been dreaming about such a mission.
This is an unprecedented mission which will act as a real game changer for many of the applications in the Copernicus surfaces. As the sea ice retreats each year, and we can measure that with a 40-year record of microwave radiometer measurements from space, we see profound changes in the Arctic. As sea ice forms, it forms freshwater ice. That means that it rejects the salt that is in the ocean, but the salt is rejected as very dense brine. And this is heavy, and it sinks to the bottom of the ocean, driving the thermohaline circulation of our ocean globally. So when we see a diminishing sea ice, then we can expect profound changes in our ocean circulation. My name is Craig Donlan. I am the head of the Earth Surface and Interior at the European Space Agency's Technology Centre, ESTEC, in the Netherlands. CIMR stands for the Copernicus Imaging Microwave Radiometer. CIMR will provide measurements of sea ice concentration, sea surface temperature, and wind speeds, and even wind vectors in the Arctic in near real time within 1 hour of reception. And this will be broadcast to ships who are operating in that region as part of the navigation safety. At the same time, we will be on the land able to measure soil moisture. We will also measure snow parameters, which are very, very important for freshwater. We need to understand the snow-water equivalent, how much water we can expect from the snow when it melts, which recharges our reservoirs, and also is important for hydrology applications around the world.
Being a radiometer, that means that it's a passive instrument, and we're listening to the natural radiation that is coming from our planet. But we're listening with many ears, or frequency bands. And each frequency band is telling a slightly different story about our Earth and its climate system. It's designed to measure both sea surface temperature and sea ice concentration simultaneously and at very, very high spatial resolutions. We're talking about less than 5 kilometers for sea ice concentration and 15 kilometers for sea surface temperature. My name is Rolf Midhassel, and I'm the payload manager, the instrument manager of CIMR. This is a crucial capability for understanding the evolution of the climate in the polar region, which is particularly sensitive to changes in sea surface temperature and sea ice coverage. CIMR will also have a wide swath width, which means it can cover a large area of the Earth's surface with every single pass. However, the instrument also includes many other novel technologies. In total, we have about 50 full receiver chains. This to make sure that we cover the Earth fully and we can see every part of the Earth as we rotate. And each receiver chain has its own digital processing capability. And that allows us to remove interference, so unwanted signals coming from man-made systems, so that we can really focus on what is coming from the Earth.
I'm Claudio Galeazzi, and I'm CIMR project manager at ESA, ESTEC. Now, what I'm going to explain to you in simple words is what is really unique in CIMR. Visible mesh is made of a very thin wire, thinner than my hair, 1,700 kilometers of molybdenum covered by gold. Yes, this gold is quite precious. Now, imagine such a mesh extended for a surface of 50 square meters, which is a medium apartment. You deploy in space at 800 kilometers apart from Earth. You give a shape of a parabola, extremely accurate. Accuracy is below 1/3 of a millimeter. And then you have created an antenna.
For CIMR, we build a special type of satellite that carries, powers, manages the rotating instrument mounted on top and sends all scientific data to Earth. In order to achieve the required performance, the satellite is equipped with a scanner mechanism that makes the 700-kilogram instrument rotate at 8 revolutions per minute. It is like having a small car, a Fiat 500 that rotates on top of a platform.
While rotating, we have to maintain the shape within a fraction of a millimeter. This is a major challenge, And to achieve it, we have more than 1,000 control points. That's basically ties that connect the surface and pulls so that we get the shape that we need. The combination of surface accuracy, the size, and the rotation makes this the most challenging mesh antenna ever developed for space.
All will be deployed because it would not fit in a fairing of a normal launcher. So the mechanism of a satellite are really complex to ensure such a deployment is safe.
The rotating part is generating an angular momentum around the axis that needs to be counterbalanced. Otherwise, the entire spacecraft would start to spin. Instead, we need to keep a 3-axis stabilized spacecraft attitude to maintain the sun pointing of the solar panels that will generate the required energy. My name is Mario Straggianese. I am the CIMR Satellite Engineering and Heavy Manager. The overall generated momentum is around 1,000 Newton meter per second, so it's quite big. And to counterbalance this momentum, there are no big single wheels on the global market. This is why we need to think about a smart way to design the momentum compensation system. We can use either more little wheels or eventually a single bigger one that we would need to design ad hoc for CIMR. Imagine a spinning top. Sometimes you see that the top of the axis of rotation makes circles, and this is called nutation. We have to avoid this because it would affect the scanner mechanism, it would stress it, and also it would affect the antenna pointing and the overall performance. But how do we do it? There is nothing else than balancing the weights. So first we will do an accurate balancing process on ground that is performed at each subsequent integration phase. However, small residual variations in the mass distribution might still occur when the reflector deploys in space, and we cannot fully test this on ground. Another challenge is how to transfer from the rotating part to the fixed part not only power, but also all the payload data. This is because several functionalities are located on the platform. The whole satellite is 14 meters tall. It is like 6 floors building, and the overall mass is 2 tons. CIMR is a big spacecraft. However, we need to make a certain level of optimization to fit into the fairing of Vega C and to comply with mass versus performance requirement. So we need to fit a 14 meters tall spacecraft consuming almost 2 kilowatts of power into the usable volume inside the Vega C fairing. When stowed, the spacecraft is 5 meters tall and 2.5 meters wide.
Once we get the data from the satellite, this is not the end of the story. We have to make them usable for the scientists. This involves a large work in processing and distributing them. My name is Marcello, I'm Italian, and I'm an engineer here in ESA. The data processing typically is done in 3 steps that we call level 0, 1, and 2. The level 0 is easy. We just get the data from the satellite and we change the format to make them readable. Basically, we transform them from a string of zeros and ones to actual numbers that you can read. Then we have to make the numbers sensible. This is the level 1 that gives the data that are the basis for the scientific evaluation. The first thing we do in level 1 processing is geolocation. We write in the data the exact location on Earth where the data was taken. It seems easy, but it's not, because we want to know where the antenna was looking while recording the data to within few hundred meters. But the satellite is 800 kilometers away from the Earth, like Amsterdam to Munich, for example. To do that, you have to know the orientation of the satellite, the rotation of the scanning antenna, and the deformation of the antenna. Then we correct the data for the known errors. For example, we have to correct for the real shape of the antenna. And that's very important. In fact, to maintain the performance of the instrument, we have to recalibrate the instrument at each rotation. For example, one important product of CIMR is the measurement of the sea surface temperature. But we do not receive from the satellite the sea temperature measurement directly, because we measure radiation. CIMR is not a thermometer, but a radiometer. So from the radiation, we have to understand the temperature. As an analogy, just think that you want to measure the temperature of an iron rod, not with a thermometer, but by looking at how red it is. All the processing from level 0 to level 2 is done by the Copernicus ground segment within 3 hours since the time the data has been taken by the satellite. This involves a very large and fast computational capability. The ground segment then distributes all data to the scientific community that will use them together with the data from the other satellites to actually develop their climatology and meteorological models. This might just be one of the most advanced Earth observation satellites in the world. We are today in a position to say that we are really pushing forward the frontiers of remote sensing technology with this mission.
We need new policies, and for that we need evidence. And once those policies are implemented, we need to monitor their impact, not just in the Arctic, but globally. And that's what the CIMR mission is designed to do. It's designed to bring the evidence base for policymakers so that they can do their job.
CIMR is a very large and complex enterprise. In simple words, I would brand it as made in Europe. The prime contractor is Thales Alenia Space Italy from Rome. The instrument prime contractor is OHB Italia Milan, while the big antenna is made in Munich from HPS and LSS, two small medium enterprise. And this is also a record for CIMR because the involvement of SMEs is unprecedented. CIMR satellite is due to be launched in early 2029, which seems you very far from today, which is not the truth. It's pretty normal for such a complex missions.
The measurements made by CIMR will be used by a number of different services and users around the world. First and foremost, the sea ice services of the world, which are charged with providing information to shipping and other applications in the Arctic and the Antarctic. So CIMR will be a workhorse for those services. Also, it will provide information for the Copernicus Marine service. It will be a fundamental measurement of salinity, of temperature, of sea ice, and of wind vectors. These are the key parameters that drive our ocean circulation from the surface down. So really a fantastic input to those services. Then for climate services and for climate modeling teams, we will have an unprecedented record that we can extend from the current record developed from different sensors over the years, taking us through to the next 15 to 20 years, depending how long each CIMR satellite lasts. Each satellite is meant to last for 7.5 years at least, with fuel for 12 years on board. So we really are expecting a great data set from CIMR.